A patient sits in your exam chair, their eyes darting rapidly in every direction. To the naked eye, this movement looks entirely random. You cannot confidently diagnose the underlying cause by simply watching the physical eye. We have to freeze the motion and extract the exact geometric data. This real-time trace is an electro-oculogram, plotting the pupil's position over time. The clinical challenge is taking these jagged, two-dimensional lines and translating them into a precise, three-dimensional map of lesions in the brainstem and cerebellum. These rhythmic patterns function as precise neurological biomarkers, encoding the physical and electrical state of the brain's internal architecture. Every differential diagnosis for an oscillating eye comes down to a single kinematic metric, the initiation phase. Look closely at the nystagmus pathway. The initial movement is a slow drift from baseline, representing a mechanical failure to hold steady gaze. Now, the saccadic oscillation pathway. It initiates with a purely fast, sharp spike. There is zero drift. It is the difference between a system that is physically unable to hold a position and a system suffering from rapid neurological misfires. Identifying this initiation phase incorrectly sends the clinical investigation down a different neural pathway entirely, leading away from the actual site of the lesion. Let's focus on the nystagmus pathway. The exact curvature of that slow drift tells us precisely which neural circuit has failed. This graph displays linear velocity nystagmus. The blue trace travels away from the center in a perfectly straight line, followed immediately by a fast corrective jerk back to the target. A linear waveform indicates an imbalance in tonic innervation. It points directly to a peripheral or central vestibular lesion. If we look at this updated curve, the velocity is decreasing. The line flattens out before the eye snaps back. To understand why, we look at the brain's pulse step innervation. The brain fires a pulse of energy to move the eye and provides a continuous step of energy to hold it there. Here, that holding step fails. Without the step innervation, the physical elasticity of the orbit takes over. Like a stretched rubber band, it physically drags the eye back to the center, decelerating as it gets closer. Reading the curvature of this slow phase instantly separates an inner ear imbalance from a mechanical failure of the brain's neural integrator. This graph shows the opposite scenario, increasing velocity nystagmus. The blue drift curve accelerates exponentially the further it gets from the target. This acceleration reveals an inherently unstable integration of saccadic innervation. The eye is being actively driven away from the target. The plane of movement dictates the clinical stakes. Horizontal increasing velocity often indicates benign congenital nystagmus. If the movement is vertical, you are dealing with acquired pathology. The timing of the waveform also isolates specific anatomy. Periodic alternating nystagmus, or PAN, completely reverses its direction every 90 seconds. This 90-second cycle isolates the defect to the nodulus and uvula of the cerebellum. Because of this highly specific anatomic location, PAN responds exceptionally well to the drug baclofen. When the direction shifts vertically, we see downbeat nystagmus. The eye slowly drifts upward, followed by a fast downward corrective jerk. Downbeat nystagmus strongly correlates with cerebellar disease, midbrain lesions, or systemic toxicity from lithium or heavy alcohol use. Analyzing waveform acceleration and direction allows for the mapping of lesions to specific anatomical coordinates within the brainstem and cerebellum. We move to the second half of the diagnostic tree, Saccadic Oscillations. Here, the motor system fires without restraint. Look closely at the red trace on this graph. Notice the perfectly flat horizontal lines between the vertical spikes. There is absolutely zero slow drift. Between saccades, the eye is completely still. The most common type of micro-intrusion you will encounter is the square wave jerk. Zooming in reveals a distinct square morphology. A tiny 1-degree saccade off the target, a flat 200 millisecond pause, and a saccade right back. When square wave jerks elevate in frequency, they correlate with severe clinical conditions like Parkinson's disease, progressive supranuclear palsy, and anorexia nervosa. But these tiny square deviations are mechanically distinct from macro intrusions. Watch as the trace expands. This hypermetric overshoot represents macrosaccadic oscillations. The eye bounds wildly above and below the target, completely unable to stop on it. This massive failure of inhibition localizes the damage to severe dorsal cerebellar or pontine disease. Analyzing the amplitude of a purely fast oscillation instantly tells you if you are tracking a subtle neurodegenerative decline or an acute cerebellar stroke. Scaling up from these measured overshoots brings us to total, uninhibited ocular chaos. Historically called dancing eyes, this extreme saccadic pathology is opsoclonus. The eye darts wildly across the X, Y, and Z axes simultaneously. There is a complete lack of intersaccadic fixation. The eye never rests. Opsoclonus carries grave localizing value. It is highly indicative of neuroblastoma in pediatric populations and metastasized occult carcinoma in adults. We can contrast the multiplanar chaos of opsoclonus with a similar condition restricted to a single plane, ocular flutter. This diagram shows flutter. It shares the exact same lack of fixation as opsoclonus, but the rapid oscillations are strictly horizontal, locked entirely to the x-axis. Distinguishing whether this saccadic chaos exists in 2 dimensions or 3 often serves as the very first clinical indicator of a hidden, life-threatening metastasis. However, not all chaotic waveforms represent organic neurological destruction. You may see a patient presenting with saccades that are incredibly fast, exceeding 20 Hz. This high-frequency trace shows psychogenic flutter. It looks severe, but the warning overlay highlights the actual cause, a convergence effort. This is not a brain lesion. It is a voluntary movement driven by the patient deliberately crossing their eyes. You can verify this without a single scan. You simply wait. The human muscular system cannot sustain a 20 Hz voluntary contraction for long, and the movement will quickly fatigue. Recognizing the mechanical limits of human physical fatigue prevents massive misdiagnosis and stops you from ordering expensive imaging for a psychogenic presentation. The rules are strict. A slow drift means a neural integrator failure. Fast-only oscillations mean unrestrained motor firing. Differential diagnosis in neuro-ophthalmology relies on translating these kinematics directly into neuroanatomy. Remove the noise of the physical presentation, extract the geometric data, and trust the waveform. The resulting waveforms provide a quantifiable record of the mechanical and electrical stability of the central nervous system.